Hello, this is Mr. P, and today we're going to learn about solving exponential and logarithmic equations. We're finally going to put all these properties to good use and manipulate some equations to solve them for the variable. This section will be mostly problems. I'm going to show you different techniques and ways to solve different types of problems. So starting with our first problem, which is an exponential equation. Here, one of our strategies we can use is if you are able to rewrite any of the numbers so that they have the same base, then you can use some of those properties we saw in the last section. For example, if you recognize that 81 is 3 to the 4th power, then you can rewrite it as 3 to the x plus 1 equals 3 to the 4th. And then you should recognize that the only way for these two to be equal, if the bases are equal, is for the exponents also to be equal. So we can ignore the bases and focus just on the exponents. So x plus 1 is equal to 4. And then we just subtract 1 from both sides. We get x equals 3. Now once you have an answer, you do need to plug that back into the original equation to make sure that it works. And now that you're starting to work on problems other than just a linear equation, a good rule of thumb that will serve you well is that treat all solutions like potential solutions until you check them in the original equation. So if we substitute in 3 for x, then in the exponent you get 3 plus 1 is 4. So 3 to the 4th is 3 times 3 times 3 times 3, which is equal to 81. So yes, our answer does check out. So that's something to always keep in mind and just good words to live by. When working any equation other than a linear equation, treat your solutions as potential solutions until they're verified in the original equation itself. Alright, so let's let you try one and go ahead and pause the tape here. Go ahead and work that problem and solve for x, and we will go over it in a moment. Okay, hopefully you have your answer, and first thing we want to do, just like the last one, is see if we can rewrite it so the bases are the same. Well, hopefully you recognize that 4 is 2 squared, so our equation just becomes this. The left side doesn't change, right side we just rewrite it as 2 squared. And now since the bases are the same, that means the exponents must be the same for those two powers to be equal to each other. So 2x plus 1 has to be equal to 2, and then we're going to subtract 1 from both sides, divide by 2, and we get x equals 1/2. And if you do check it in the original equation, you'll see that it does work. All right, let's look at one that's a little different. And again, we're going to be doing some rewriting here. This one's a little more intimidating. We have e to the negative x squared equals the quantity e to the x squared times 1 over e cubed. Well, notice in the first two terms we definitely have e to some power. And then in the third one, though, we have e in the denominator. So I want to try to rewrite that. The first term isn't going to change at all. The second one, when we have a power raised to a power, we keep the base and multiply the exponent. So this is going to be e to the 2x. And then the last one, I can rewrite 1 over e to the third as e to the negative 3. Remember, negative exponents have nothing to do with negative numbers. They mean reciprocation. So this is my new equation. And now on the right side, I can further combine that because I am multiplying powers. So when you multiply powers with the same base, you're going to keep the base and add the exponent. So 2x plus a negative 3 is the same as 2x minus 3. Now we have a single exponential on both sides. And we have the same base, so that means that the exponents must be the same. So we simply have negative x squared equals 2x minus 3. And now we have a quadratic equation. And our first approach for a quadratic equation should always be set it equal to 0 and factor. So if I move the x squared over to the negative x squared over to the right, it becomes a positive x squared. So I have x squared plus 2x minus 3 is equal to 0. I know I moved it on to the right, but then I rewrote it, all three of them on the left. And now we want to go ahead and factor, and by now you should be able to factor this. It's going to be x plus 3 times x minus 1 is equal to 0. And then we're looking for the value of x that causes each factor to be 0. So the first one would be -3. The second one would be a +1. So those are my two potential solutions. Remember, treat all solutions as potential solutions until you check them in the original equation. But you'll find that when you do substitute them in, that they do both work. Therefore, your solution set is -3 and +1. We're going to be getting into problems where there are going to be multiple answers, and we're going to be speaking about solution sets of those equations, especially when we get into the trigonometry equations. All right, so let's look at one of those that you can do. I'm going to let you go ahead and do this one. So pause the tape, go ahead and work the problem, and then press play when you have an answer. Okay, hopefully you have an answer by now. And if we look on the left side, it's just e to some power. The right side is e to the some power, and then we have e in that denominator. So I can rewrite this first one as e to the -2. The rest of the equation will stay the same, but I still want to combine these two, so I have e to a power equals e to a power. And when I do that, when multiplying powers, you keep the base and add the exponents. That gives me e to the 3x minus 2. The left side of the equation stays the same. And now we can ignore the bases, because we know that in order for this to be true, the exponents must be the same. So x squared must equal 3x minus 2. I could move the x squared over to the right, but that would give me a negative leading coefficient. So instead, I'm actually moving the other two to the left. So a positive 3x becomes a negative 3x when I move it over, and a -2 becomes a positive 2 when I move it over. And now I have a quadratic with a positive leading coefficient, which makes it easier to factor. I'm looking for factors of 2 that add up to -3. That would be -1 and -2. So this is my factored form. And then I want the values of x that cause each factor to be 0. That would be a +1 for this factor and a +2 for this factor. Now, these are my potential solutions, but again, when I substitute them in the original equation, you'll see that they do both work. Therefore, that is my solution set. All right, now I want to talk a little bit about the theory of the symbolic manipulation, something that helps us to get away from the meaning of the symbols we're pushing around, so it can be a more visual experience. For example, if we look at our simple algebra, if I had the equation 3x equals 9, and the question is, how would I solve it, and why would I do it that way? Well, we've been taught in algebra to isolate the variable. So whatever's happening to the variable, we need to undo it or move it to the other side. So with the how, we're going to definitely divide both sides by 3. That's how we're going to solve for x. But the question of why do we divide by 3? Why division is a more important question. And the reason is, you look at what's happening to the variable is multiplication. That's what needs to be undone. So we undo multiplication with division, we undo addition with subtraction. These are things we've been doing in Algebra 1. So here the key is we undo operations with inverse operations. Now until now, the only inverses you've had is addition, subtraction, multiplication, division. But now, as we've seen in the last couple of sections, logarithms are the inverse operations of exponential functions. So here we can take a look at the fact that exponentiation cancels out logarithms, and logarithms cancel out exponentiation. And we can see that in some of the properties, some of those inverse properties that we saw in a previous section. So a to the log base a of m means that these can cancel, leaving just the m. And similarly, the log base a of a to the r means these can cancel, leaving just the r. That's because exponentiation cancels logarithms, logarithms cancel exponentiation. So you can take more of a visual approach and get faster at these manipulations if you're not worried about the meaning behind the logarithms. It's important to know the meaning. Logarithms are exponents. It's important to know that. but your symbolic manipulation can get a little faster. So let's look at the original definition of logarithms. Log base a of x equals y if and only if a to the y equals x. And we're going to see how this symbolic manipulation works out when we don't worry about the meanings here. I'm going to take the left equation and make it look like the right one. I'm going to take the right one and make it look like the left one. So here on the left equation, what's happening is logarithms. That's what's happening to that x. So to undo a logarithm, you use what's called exponentiation. Exponentiation is putting both of these sides as an exponent with some base. So let's choose a to be our base. We can choose any base we want, but I choose the one that's going to create a cancellation here. So this is what we mean by exponentiation. We put a base on both sides where each of the side will be the exponent of that base. So on the left side here, a to the log base a, we already know that that cancels. And then what we're left with is simply that x equals a to the y, which is what we have on this side. Likewise, on the right side, if we want to go from the exponential to the logarithmic form, you simply take the log of both sides. To go from logarithm to exponential, you exponentiate both sides. To go from exponential to logarithmic, you take the logarithm of both sides. So taking this equation, and I take the logarithm of both sides, I can choose any base I want, so I'm going to choose base a. And that gives me a nice little cancellation on the left here, log base a of a, those cancel themselves out. So it leaves just y equals log base a of x, which is what we started with originally on the left side as well. So the moral of the story here, and the manipulations get easier if you just realize the visual part of it, that exponentiation cancels logarithms, and logarithms cancel exponentiation. But of course, let's see these in some problems. So let's take a look at these two problems. And I'm going to let you go ahead and try them. Go ahead and pause the tape, or pause the video, and try both of these problems. On the left one, you're going to take the log of both sides. On the right one, you're going to exponentiate both sides. And make sure you choose your correct basis. And one more thing is we are looking for exact answers on these. So go ahead and pause now. Okay, hopefully you have an answer, or actually two answers. The first one, this is an exponential equation. We want to get at the variable up in the exponent. So what I'm going to do here is I'm going to undo that exponent by taking a log of both sides. I can choose any base I want, so I want natural logarithm, which will cancel out the e. So natural log of e, those cancel out, leaving just 2x minus 3 equals natural log of 20. Now it's important to realize that natural log of 20, that is just a number. That's just a constant. So don't get too worried about the fact that you still have a natural log there. It's just a number. So now solving for x is just like any other simple linear equation. We're going to take the opposite of the constant and then divide by the coefficient. So add 3 to both sides gives us this. And divide both sides by 2 gives us this. Now this would be our exact answer if you put if you put this expression into a calculator. It'll give you a decimal, which would be an approximation. But as it stands right now, this is the exact answer that we were looking for. All right, for the other equation, we have a natural log equation, so we want to use exponentiation to undo this. And you're going to find that you either want log equals number or log equals log. And then you can use exponentiation to undo those logs. So here we have natural log, so the base that I'm going to choose is going to be a base that will undo natural log. And that, of course, is base e. So I exponentiate both sides. That gives me a cancellation on the left. So the only thing that's left is the argument here, which is 3x minus 4 equals e to the fifth. And remember, again, e to the fifth is just some number. E is a number, and you raise it to the fifth power, you get another number. So again, we're going to add 4 to both sides, which gives us this line, and then divide both sides by 3, and we get that is our exact answer. You can put that in the calculator and get a decimal approximation, but you would no longer have an exact answer. All right, let's look at some other things that can come up. First of all, as I said before, when dealing with logarithmic equations, you want to get it to either log equals number or log equals log. Now here we have two logs that are in the same base. So if I just address the fact that I need to get rid of that 2 in the front, then I'll have log equals log. So of course we can use the power property for that. I take the 2 and move it up in as an exponent to the argument. So that gives us log base 5 of x squared equals log base 5 of 9. Now I can get rid of the logs by doing exponentiation. I can choose whatever base I want. So I want to choose a base that will cause a cancellation. Namely, I want to exponentiate with 5. So on the left and right sides, we get a cancellation on both sides, which is going to give us just x squared equals 9. So if I take the square root of both sides, I'm going to get x equals 3 or negative 3. Remember, when you take the square root of both sides, you must add the plus minus. Now, we're not quite done yet because, as I mentioned before, we treat all answers as potential answers until we check them in the original equation. So if I substitute in 3 for x, I have no problem. It does check out. But notice if I substitute in negative 3 for x, then I'll have log base 5 of negative 3, and we are not allowed to take a log of a negative number, just like we're not allowed to divide by 0 or take the square root of a negative number. So here we're going to say that negative 3 doesn't work, even though it came out algebraically to make it look like it works. So we call that an extraneous solution. Now, as a side note, you will notice down the road when dealing with complex analysis, it is actually possible to take the log of a negative number. But here we are dealing strictly with our real numbers. So for our purposes here, we are not allowed to take the logarithm of a negative number, or we're not allowed to take the square root of a negative number, and we're not allowed to divide by 0. All right, so therefore, our only solution then would be 3, so we would say that our solution set is just 3. All right, let's let you try one. Looking at this equation, and go ahead and pause, work the problem, and then I'll be with you shortly. Okay, hopefully you have an answer to the problem by now. What's keeping this from being log equals log are the coefficients in front. So we can move the coefficients up into the exponent by using that power property. So here, move the 2 up into the exponent, move the 3 up to the exponent, and we would get this. Next, we want to undo the logarithms. But before I do that, actually, notice here we have 4 to the third. That is a number that can be evaluated. So let's go ahead and do that. I'm going to rewrite 4 to the third as 4 times 4 times 4, which is 64. So we have log base 5 of x squared equals log base 5 of 64. And now both logs are in base 5, which makes the exponentiation doubly good because we get a cancellation on both sides. So we have just left x squared equals 64. And of course, when we take the square root of both sides, don't forget the plus minus. And then when substituting to check your answer, the positive 8 works, no problem. But notice how the negative 8, if you were to substitute that, you'd be taking the log of a negative number. Therefore, the negative 8 is extraneous, and our solution set is just positive 8. All right, now sometimes you have to do a little more work in order to get to log equals log or log equals number. Remember, those are our goals, is to get one of those two, then we can exponentiate. So let's take a look at this problem. Here I have log, log, and number. So I can either have log equals log or log equals number. But since these are both the same base and they have a plus between them, I can easily combine these to be a single log expression. So that would be the product property because of the plus. So it's simply going to be log base 4 of the product of those two arguments. And that is equal to the one on the right side. We didn't change that. So notice how I have log equals number. And then to undo that log, we're going to use exponentiation. I can choose whatever base I want. So I'm going to choose base 4. So we exponentiate both sides with 4. On the left side, I have a nice little cancellation. So therefore, just what we had in the argument, which are those two parentheses, equals 4 to the first power, which is just 4. If I multiply this out, if I distribute that, I get this trinomial, negative x squared minus x plus 6, and then the right side is just 4. This is a quadratic equation, so our first attack should be set it equal to 0 and factor, if you can. And if we subtract 4 from both sides, I get this is now set equal to 0, but I have a negative leading coefficient. You can factor with a negative leading coefficient. Personally, I don't like to do it. Sometimes I find it confusing, so I just like to go ahead and multiply through by -1, which gives me this line. And now it's much easier to factor without any hassle. The negative x becomes a positive x, the negative 2 becomes a, positive 2 becomes a negative 2, and the negative x squared becomes positive x squared. And 0 times -1 is still just 0. So now in factoring, I want factors of -2 that add up to a +1. Well, that would be +2 and -1. So therefore, my potential solutions are the values of x that cause each factor to be 0. So in the first one, you have -2. In the second one, you have a +1. But like we said before, these are just potential solutions. Now you might be tempted to look at the -2 and say, hey, it's negative, so it must be extraneous. But don't jump to conclusions. You have to actually check them in the original equation. And notice how if x is -2, -2 plus 3 is 1. It's still a positive number. And 2 minus a -2 is 2 plus 2, which is 4, which is still a positive number. So we have no problems such as taking the log of a negative number. So you'll actually see when you substitute both of them in that they do actually both work. Therefore, the solution set is both -2 and +1. So you definitely don't want to jump to any conclusions about your answers. Just go ahead and check them in the original equation, and then you'll see whether or not they are extraneous. All right, let's look at one that you can try similarly. And go ahead and pause the tape, work the problem, and I'll be right back with you. All right, hopefully you have an answer by now. If we look at this, I have log, and number, so I do have a plus. Both logs are a common log, same base, so we can combine these using, again, the product property because of the plus. If that was a minus, we would use the quotient property. But we do have a plus, so this is simply going to be the log, the common log of the product of the arguments. So common log of x times x plus 15. Now I want to undo the common log. Even though you don't see a base written here, that means it's common log, which is base 10. So I'm going to exponentiate both sides with 10. That would give me the cancellation on the left side. So that leaves me with x times the quantity x plus 15 equals 10 squared, which is 100. So if I distribute on the left and then I bring the 100 over to the left side, which makes it negative, then I have a quadratic that is set equal to 0. So now I can factor. I want factors of -100 that add up to 15. That would be +20, -5. So this would be how I would factor it. And now I want the value of x that causes each factor to be 0. So it would be +5 and -20. Those would be my potential solutions. And we're checking in the original equation. 5 does work, but when I go to plug in 20, notice I get log of a negative number here and also log of a negative number here. So 20 is definitely extraneous. That one will not work. Therefore, our solution set is just +5. All right, now I'm going to introduce you to a little more of an advanced technique that you will be seeing a lot in calculus. It's called U substitution. Let's look at this exponential equation. First thing we want to do on an equation like this is if we can ever rewrite exponents so they have the same bases, then that gives you more options with your manipulations. So since 4 is 2 squared, I'm going to rewrite it as 2 squared. So it's 2 squared to the x minus 2x minus 12 equals 0. And then what I'm going to do is I'm going to switch the order here because a power to a power means you keep the base and multiply the exponents. So I'm just going to rearrange them so I have 2 to the x being squared minus 2 to the x minus 12 equals 0. And now I'm going to use a technique called U substitution. If you have something that's making your equation a little complex, you can let U equal that expression, or equal a part of the expression that's making it tough on you, and then substitute in the U, and sometimes the math is easier to see. So for U substitution, this 2 to the x is what I see twice here. So I'm going to let U equal 2 to the x. So making my substitution, this becomes U squared, this becomes U, and I end up having this equation, which is you should recognize as a simple quadratic set equal to 0. So we factor factors of negative 12 that add up to negative 1. That would be negative 4 and positive 3. So now I want to find the value of x that causes each factor to be 0. So in a sense, I'm going to take the factor and set it equal to 0 and solve for x. Well, this is where we no longer want the u, so we want to back substitute. Since u was 2 to the x, this becomes 2 to the x minus 4, and that I'm going to set equal to 0. That way, solving this equation will give me the value of x that causes the factor to be 0. So it's going to be that for the left one, or don't forget that we have two factors here. So since u is 2 to the x, it's going to be 2 to the x plus 3 equals 0. So now I have two equations that I can now solve. On the first one, the left one, I'm going to add 4 to both sides. Gives me 2 to the x equals 4. And hopefully you can just recognize that, well, 2 squared is 4, so x should definitely be 2. Yes, I can rewrite 4 as 2 squared, take the natural log, or take the log base 2 of both sides, get the cancellation on both sides, I'll have x equals 2. But hopefully you recognize 2 squared is 2. Now on the right side, when I subtract 3 from both sides, I'll get 2x equals negative 3. But the problem in here is 2 being a positive number, if I raise it to any exponent, it doesn't matter what exponent I raise it to, it will never result in a negative number. Because remember, a negative exponent has nothing to do with negative numbers, it means reciprocation. Therefore, this equation actually has no solution to it. So we're going to say no solution. We're going to use the empty set symbol to say no solution. So therefore, our only answer would be the x equals 2. That is our solution set. And if you check it in the original equation, it does check out as well. All right, so that's called U substitution. I also want to show you another technique, and something where you have this type of equation. If you have a variable up in an exponent and your bases are different and you have no way to rewrite them as the same base, then we're going to use the fact that logarithms undo exponentiation. Or we're going to use our old friend, the power rule, in order to pull those exponents out of in order to pull those variables out of the exponents. So here we have a variable in the exponent. Our bases are not the same, nor can they be rewritten the same. So we're simply going to take the log of both sides, and I can choose any base I want. And I could choose base 2, but since I can choose any base I want, I usually choose natural log, because that's what I'm used to working with, and that's what in the future you will become used to working with. So here I take the natural log of both sides, which means I can now use the power property to take the x and bring it out to the front as the coefficient. So we have x natural log of 2 equals natural log of 5. Remember, natural log of 2 is just a number, so if I divide both sides by that number, I get that as my exact answer. And another reason why I like to choose natural log of when I'm choosing what base to work with is because if I did need a decimal approximation, then I can just put this equation or this expression into the calculator and I'll get 2.322. So it's approximately equal to that. All right, so let's let you try one. Looking at this equation, we have 2 to the x equals 10. Go ahead and work the problem. Get an exact answer. I also want you to give me a approximate answer to 3 decimal places, and then press play when you have your answer. Okay, hopefully you have an answer by now. We want to get at that x up in the exponent, so we're going to take a log of both sides. I chose natural log. And this allows us to take the x and move it out to the front using the power property. So x natural log 2 equals natural log of 10. Divide both sides by natural log of 2. That would be your exact answer. And then if you put that in the calculator and round it, you're going to get approximately 3.322. So hopefully you got that one. Now this same technique of taking the log of both sides and then using the power property to pull the exponent out into the front, that even works when you have more complicated expressions in your exponents. For example, let's look at this very, very intimidating problem. Now, if we had both of them had the same base.
I just want to let everyone know my client operation is going to do their thing, so parking lot could be empty if you'd like it that way. Okay, have a great weekend.
Okay, sorry for the interruption, but as I was saying, if the bases were the same, if they were both 5s or both 3s, then we could simply set the exponents equal to each other. Or if we could rewrite them so they were the same bases, we could do that. But we don't have that option available to us. So to get exponents out of, or to get variables out of the exponent, we need to use logarithms. So again, I'm going to take the natural log of both sides because I like dealing with natural logs. And now using the power property, I'm going to take x minus 2 and move it out to the front. And I'm going to take 3x plus 2 and move it out to the front of this one. So that gives us the quantity x minus 2 times natural log of 5 equals the quantity 3x plus 2 times natural log of 3. Now, it might be confusing as to where to go here, but remember, natural log of 5 and natural log of 3 is just a number. So I'm going to distribute here. And when I distribute, I'm going to get x natural log of 5 minus 2 natural log of 5. And when I distribute here, I'm going to get 3x natural log of 3 plus 2 natural log of 3. Now I have 4 terms. 2 of them have x and 2 of them do not have x. The 2 that don't have x, they're just constants. Remember, even 2 natural log of 3 is just some number. So my strategy here, and hopefully you've seen this strategy before, is I'm going to put all the terms that have x on one side, all the terms that don't have x on the other side. So if I move the 3x natural log of 3 to the left, then it becomes a minus. If I take the minus 2 natural log of 5 and move it to the right, it becomes a plus. And this is my new equation. Every term on the left has x in it. Every term on the right does not have x in it. So since every term on the left has x in it, that means x is common to each term. Therefore, we can factor it out. So factoring out a common x leaves x times what remains, which is natural log of 5 minus 3 natural log of 3. And the right side remains the same, which is all just one number. So what's in parentheses is also just a number, so I'm going to divide both sides by whatever that parenthesis is, and that's going to give me an exact solution of x equals this very, very intimidating looking number, but it really is just a number. And if you put this into the calculator and get a decimal approximation, then you should get approximately negative 3.212. Now, one thing I do want to say is I see a lot of errors putting this one into the calculator. Remember that it's the entire numerator divided by the entire denominator. So when putting in the calculator, you should open a parenthesis here, close a parenthesis there, open one here, and close one there. Or in other words, I'll show you what it should look like properly in the calculator. It's the entire numerator divided by the entire denominator. So if you enter it correctly into the calculator, then you will get a correct answer, and rounding it to 3 decimal places, you will get that. All right, let's let you try one last problem, and it'll be similar to this style. And here's your intimidating looking problem. It's 1.2 to the x equals 0.5 to the negative x. And let's go ahead and let you do this and round it to 3 decimal places. Go ahead and pause now and work the problem. Okay, hopefully you have an answer by now. And of course, first thing I want to do, I want to get at those variables in the exponent, so I'm going to take a log of both sides. I choose natural log. But like I said, this can be done with any log. But when I choose natural log, now I have a way to pull that x out of the exponent using the power property. And same thing with the negative x, I'm going to pull out front to be a negative x as the coefficient. So we have x times natural log of 1.2 equals negative x times natural log of 0.5. And now I have two terms, they both have x in them, so let me pull the term on the right over to the left side, which would make it positive. And then on the right side, there would be nothing left, so that would be 0. Alright, so I have two terms, they both have x in it, so I'm going to pull out the common x. Sorry about that. And that gives the x times this fancy number is equal to 0. So divide both sides by that fancy number, and you get just x equals 0, because 0 divided by any non-zero number is just 0. And of course, when you check it in the original equation, it does work. So we are done. And that is the end of the solving exponential and logarithmic equations.